Matter. It makes up everything that we see around us. This lab coat, made of matter. This person, also made of matter. Literally anything that you can point at is made of matter. But matter also has a counterpart, antimatter. Most scientists agree that when matter was created at the start of the universe, an equal amount of antimatter should also have been created. Now, this means... "'Tis I, the Anti-Jarrah, and I am here to destroy you, and all that you learn." Okay, so to start off, antimatter versions of people don't exist. And more to the point, you're not made of antimatter, you're me standing in front of a green screen after being flipped around so that the audience can tell who's who. Oh. But since you're here, I may as well tell you about this stuff. You can think about antimatter and matter like two pawns on a chessboard. They act in the same way and do the same things, but the pawns move in the opposite directions. Antimatter is a bit like this. At first glance, a particle and its antiparticle might seem very similar. For example, they have the same mass, just like a black and a white pawn have the same size. But some of their properties are the exact opposite. Like what? Well, basically, if a particle has a property where the opposite can exist, then its antiparticle will have that opposite property. For example, all particles have a property known as chirality, which is related to the movement of the particles and influences how they decay or disappear. Now, particles can either be left chiral or right chiral. And since left is the opposite of right, if a particle is left chiral, its antiparticle will be right chiral. Is that all the differences? Well, there's one other main difference. When matter and antimatter collide, they annihilate. Now, what this means is the matter and the antimatter both disappear, and a huge amount of energy is released. And I mean a huge amount of energy. 1 kilogram each of matter and antimatter could produce nearly the same amount of energy as 3,000 nuclear bombs. That's a lot. But wait, you said that there's basically no antimatter in the universe. But if matter and antimatter were created in equal amounts, how can we possibly have more matter than antimatter? The simple answer to this question is, we don't know. But we do have theories. Like what? Well, to start off with, the universe isn't fair. Now, you might have heard that saying before, but in reality it goes far deeper than that. Let's say that we have a particle and an antiparticle. Let's say that the particle is left chiral, so the antiparticle will be right chiral. Now, intuitively, you'd assume that these two behave basically the same way, right? Yeah. Well, you would be wrong. Follow me. This is the Super Kamiokande Observatory in Japan, which was designed by some very clever people to detect some really small particles called neutrinos. But it was adapted a little for a recent experiment. The scientists at this facility fired some neutrinos and antineutrinos at the observatory and measured how many arrived. But the results of this experiment showed something really surprising. The same number of neutrinos and antineutrinos were fired, but far more neutrinos actually completed the journey. The current theory explaining this states that antineutrinos tend to decay faster than neutrinos due to the opposite chiralities. Now, this is crazy. The universe seems to prefer left chiral over right chiral, and that's likely what allowed matter to outweigh antimatter and allow the universe as we know it to exist today. So what you're saying is that antimatter is like matter that has some opposite properties, and that equal amounts of matter and antimatter were created at the start of the universe, but the universe somehow prefers matter over antimatter, and that's why we didn't blow up and disappear? Yeah, that's basically it. Wow! Science is so awesome. High five!
No.